All right, so this is section 2.3. It's called Characterizations of Invertible Matrices. So we're going to use things we figured out about inverses and apply it to other things that we've already done. So we already figured out that if you take the determinant of the matrix and you get 0, that matrix is not invertible, right? And if it's non-zero, then it is. And if it's invertible, it has to be square. And if it's an invertible square matrix, then when you row reduce it, you get the identity matrix, right? So we know things from our previous sections about row reduce a matrix and get the identity. We have all these different properties, and all these properties are equivalent. It doesn't mean they're the same. It just means that when one of them is true, they're all true, and if one of them is false, they're all false. So to show any of these is true, all you got to do is just find one of them that's true. See if you can show that one of these is true, and then you get them all automatically. So the first one's A is invertible. If A is invertible, it's also row equivalent to the identity matrix of the same size. It's always going to have n pivot positions. If it's a 3x3 matrix, when you row reduce, it's got to have 3 pivots. Ax equals 0 has only the trivial solution, right? That's true. If you row reduce it, you get the identity, so then it's row equivalent to the identity. So if you row reduce the identity, Ax equals 0 only has 0 as the solution. The columns of A are linearly independent. Ax equals B is consistent for every vector in Rn. So you could plug in anything you want to the right side of Ax equals B. You can plug in any vector that's in Rn and you'll get a solution, because the left side will reduce the identity. You'll get a unique solution, and whatever you get on the right side will be the solution. The columns of A span Rn, so these two go together. If you can plug in any vector in Rn and get a solution to this equation, that means the columns of A span Rn. That means you can come up with a linear combinations of the columns of A to get any vector you want in Rn. So if A is 3x3 and it's invertible, then the columns of A span R3. Okay. The linear transformation that maps a vector x into A times x maps Rn onto Rn. So we talked about if you have a transformation and it maps a domain, let's say Rm, into a codomain Rn, right? And we had a separate thing called the range. The range was the actual vectors that this transformation maps into. Well, if A is invertible and it reduces the identity and all that other stuff, that means if you're multiplying A times x, because it spans Rn, that this codomain is also the range. There's nothing in the codomain that's not also in the range. Those two are the same. So that's why when we write onto, that means it covers the entire space. So the range covers the entire codomain, right? And there's an n by n matrix C such that C times A equals I, and there's an n times n matrix D such that A times D equals I, and the transpose is also invertible. These two, you can always use the inverse. Right? If A is invertible, then you can use the inverse to do that. Right? So there's always at least one of those, but you might be able to find another one. Maybe. So we just have to remember that all those mean the same thing. Yeah, we know one exists because we have the inverse. The inverse is the only one that works both ways. So you can multiply it on either side and get the identity. Okay. And it may be the only one, I'm not sure, but the way that's worded, there might be others. So the next one says use theorem 8 to determine which of the following matrices are invertible. And it says use as few of calculations as possible and justify your answers. So is the first matrix invertible? No. So it has this middle vector, that's the 0 vector. That means you can't get 3 pivots when you row reduce this, right? So it does not row reduce to the identity, so it's not invertible. Right? The columns of A are not linearly independent, they're dependent. So this is no. Yeah. If it reduces and you get a free variable, yeah. You don't get a pivot in every column, right? You get a free variable. What about this one? So there's a bunch of ways, right? We could take the determinant 1 times 0 minus 2 times 0. That's just determinant zeros. Or you could say the second vector is a multiple of the first vector, right? The second vector is 2 times the first vector. So they're dependent vectors. So that's a no. What about the next one? This one, because it's triangular, will reduce to the identity. This is, whoops, it's not the identity. There we go. That one reduces the identity because it's form. You know, I can use this 2 to make those zeros, right? And these zeros are not going to affect any of the other rows below it, right? So I can just make that a 1 and boom, boom, hit those and make them 0. And I don't affect anything else. And then I can take this 1 and make that a 0. And because the 5 here beside it is now a 0, it's not, you know, these 2 zeros are not going to affect these 2. And then I can make that a 1, right? So I know that it reduces that way without having to actually do it. I don't have to work it out, okay? So that one reduces to the identity. So that's a yes. If it reduces the identity, then it's invertible. I don't know what the inverse is. I just know I can find one. What about the last one? So I don't know by looking at it. So let's try row reduction. So let's take that 1 and make that a 0. So replace row 3 with row 3 plus 3 row. And notice I'm not putting it in my calculator because it said to use as few calculations as possible. So I'm going to do as few as I can and see if I can figure it out before I get all the way to RREF. Right? Use RREF in the calculator, it'll do all the calculations we need. Right? Okay, so negative 3 plus 3, 6 minus 15, 1 minus 12. Let's use this 3 to make this negative 9 a 0. And then it'll be triangular, right? So replace row 3 with row 3 plus 3 row 2. So this is negative 11 plus 12, so that's 1. That's triangular, right? So for the same reasons the one above it was invertible, now this one is, so this is a yes.
How you find most of them?
Yeah. You know, you can always do that. You can always put it in the calculator, row reduce it. If it's the identity, it's invertible, okay? But there are some things that are quicker than that. Right? If you see the determinant 0, then just stop there, right? If you see you have a column of 0, stop. If one column is a multiple of another column, stop, right? So you get dependent columns. That can't row reduce the identity, right? It's already row reduced. This is row reduced right here. But if one column is a multiple of another, they're dependent, and they can't row reduce the identity. Yeah, you'll have a free variable if it's dependent, yeah. Right. To the identity. You won't have n pivots, right? Yeah. So you'll have problems on your tests that'll say, in your quiz, it'll say, determine if they're invertible, use as few calculations as possible. I don't expect you to throw them all in the matrix every time. You should not do that in the matrix. You might be right. There's always a determinant. It's if the determinant is 0 or not. If the determinant is not 0, it's invertible. Yep. Right. So that actually is not on this list here, but we're going to add it. We're going to add that to our list. That determinant is not equal to 0, is equivalent to A being invertible. All right, so a 2 by 2 matrix, and we're going to use a generic matrix A, B, C, D, is invertible if and only if the determinant AD minus BC is non-zero. So we're going to figure out on this example what A will we plug in that would make the determinant equal to 0. And we're going to not let A be that number, and then we'll have an invertible matrix as long as A is something else. So we just calculate the determinant, A times C. I'm going to subtract, which is negative 8. And I set that equal to 0. I'm going to solve that equation. So that's 3A plus 8. So 3A is negative 8, and A is negative 8/3. So if A was negative 8/3, that matrix would not be invertible. So we're going to say this matrix is invertible if and only if A is not negative 8/3. If A is not negative 8/3, then it's invertible. If it is negative 8/3, you'll get a determinant of 0, and it would not be invertible. Side note, we talked about singular, non-singular, right? So if a matrix is singular, that means invertible. And if it's invertible, that means you get unique solutions to AX equals B. Right? Non-singular means it's not invertible. You get infinite meaning, right? Or none. Make sure that I'm saying that right. I get confused. Non-invertible is singular. Yeah, I messed that up. Okay. Let's scrap that. Sorry. Yeah. So singular means non-invertible. And non-singular means invertible. Invertible means all that stuff on that list, right? Or you get only the trivial solution to x equals 0, you get unique solutions. If it's singular, you're going to get either no solution or infinitely many to ax equals b, and ax equals 0, you'll get infinitely many.
So singular is like just a description of all that. It's not really like a form or a matrix or whatever.
No. It's just a word that means non-invertible. Okay. So if A and B are invertible, then the inverse of the product is equal to the product of their inverses, but you reverse the order. So the inverse of A times B is B inverse times A inverse. So we're given A inverse, B inverse, and we're asked to find the inverse of AB. So the inverse of this product, inverse. And we're given those. So we just multiply those in the opposite order from AB. So that's 14 minus 3. 8 minus 2. 21 minus 9. And 12. 21 plus 9, sorry. 21 plus 9. 21 plus 9. 30. This doesn't feel like Wednesday. I thought it would just feel like the same as a Wednesday, but it doesn't. It doesn't feel like Wednesday. I should be on my way home right now. So I'm all messed up. 12 plus 6, 18. So that's the inverse of A times B. And we didn't even know what A and B were. Remember, you don't get a formula sheet. So it's just something you just got to know, okay? Okay. So if you have a linear transformation, any linear transformation can be written as a matrix times a vector, right? So how do you find the inverse linear transformation? So this is, we're thinking about these transformations as functions. So how do we find the inverse function, the one that'll send us back? Well, of course, it's going to be the inverse matrix. Find the inverse matrix, we get the inverse transformation. So find the standard matrix for T, find the inverse matrix if it exists. You don't always get that. And write T inverse using the notation you started with. Okay. So we have T is given by this vector. I'm going to write it in column form just to help us out, right? So that's the same as that. So this is our standard matrix A. That's the one we're call A, the standard matrix. So we need A. So what's the determinant? So it's 42 minus 40, right? Negative 8 times negative 5 is 40. So it's 42 minus 40. So the determinant is 2. So it's going to be 1/2. And then the adjoint is the matrix where we switch the main diagonal of A, and we flip the signs of the off diagonal. I think sometimes it's called the minor diagonal or something like that. So this is 7/2, 4, 5/2, 3. That's the inverse. So now I'm going to write T inverse. So 7/2 x1 plus 4x2 and 5/2 x1 plus 3x2. So that's my inverse transformation. That'll reverse whatever T does, that'll reverse it. questions?
Wrote it like that. You could also write it like vertex, like a vector.
As a vertical vector? Yeah, but it told me to use the same notation you started with, so I just wrote it exactly how it was written in the problem, you know.
But it's equivalent.
It's equivalent, yeah. This is the first component of the vector, that second component of the vector, right? It's still a vector, it's just written as a in a row instead of a column. Okay. So why don't you try this one yourself? See if you can find the inverse transformation. I'll give you a few minutes and then I'll do it. All right, so let's just go ahead and find the determinant. It's like 15 minus 12. So we get 3. So A inverse is 1/3 times the adjoint. So I'm going to switch the main diagonal. I'm going to switch the signs of the other diagonal. Sorry. So that's negative 5/3 minus 2/3. This is negative 2 and negative 1. That. And then the inverse transformation in the other notation, I'm going to get negative 5/3 x1 minus 2/3 x1. That's my, or sorry, x2. That's my first component. My second component is negative 2 x1 minus x2. So that's the inverse transformation. T is this. A is the standard matrix for T. Okay. A is the standard matrix for T. T of X, we're defining as A times X, the matrix A times X. And with that A. Right. Yeah. Inverse of the standard matrix A. That's the inverse of T, yeah. If your function was 2 times X, you wouldn't say it. Right. So T is the name of the transformation, and A is the operator. A is part of the operation that you're using. No, X is the X. A is the 2. Right, 2 is multiplying by X. Our problem A is multiplying by X. 2 is multiplying by the variable X. In our problem, the matrix A is multiplying by the variable vector X. Okay. So these aren't the same. This is just how you're computing F. You're computing T by multiplying by A. Okay. But you're right, they're like related, they're connected, but they're not the same. So let's do one more thing. Show that the inverse matrix is going to reverse what we did. Okay. So let's do this, the last one. Let's do T of 3, -2. So we're going to multiply A times 3, -2. So A was -3, 2, 6, -5. So we'll get a vector. So this is -9, -4, -13. This is 18 plus 10, 28. So -13, 28. So what it actually is this. You're plugging in this vector. Yeah, that's what you're plugging in for the vector X. And you could have written it like this. That'd have been the same thing.
Makes it a lot easier to think about.
Yeah.
Say transformation, what exactly that is. You know what I'm saying? It's sort of like.
It's a function for vectors. That's all it is.
Another matrix through this processor thing, or meat grinder, whatever. Another vector.
Yeah. Yeah. It is. Yes.
Your T is sort of like this matrix A, but it's not. It's that multiplied by A vector. When you put A vector in, you're going to get when you put A in, you're going to get another vector out.
You can get the transformation without using the matrix. You can just follow the rule here. You just do that and get it, right? You don't have to multiply by the matrix. But because we can't just multiply by a matrix, it gives us this other things that we can do, like find the inverse transformation. But not every transformation has an inverse, and not every transformation has a matrix. Just all the linear transformations have matrices. associated with them. All right, so we need the inverse now. So negative 5/3, negative 2/3. Negative 2, negative 1. We're going to multiply this by our new vector. We should get 3, negative 2, I hope. Let's cross our fingers. If it's not, then we got to go back and see what we did wrong. Okay? Yeah, we're using the previous transformation. Okay. I'm going to cheat, if you don't mind. That's 3. We don't have to do it the other one, right? So this is 26. This is negative 28. 26 minus 28. Negative 2. So this is A inverse. And this is T inverse of 13, negative 13, 28. That. Right over here. So this is T inverse of negative 13, 28. Yeah. And remember what the transformations can do, right? The transformation can find, it can rotate vectors, right? Rotate, reflect, scale. It can find derivatives of polynomials. So what would be the inverse transformation if your matrix does polynomial derivatives? Yeah. So it would do anti-derivatives, right? Should do anti-derivatives. But if that transformation is invertible, so I haven't checked that, it might be is probably it might not be because I have to think about that. Yeah. I don't remember. It was diagonal though. I do remember that it had a diagonal in it, but it may have had a column. I can't remember. That it wouldn't have an inverse. But it'd still be a linear transformation. It just wouldn't have an inverse. So some things you still say are inverses even though what you get is not a function. So like an antiderivative is not a function because you plug one thing in and you get a bunch of things out. Because you have the plus c in there, you get infinitely many antiderivatives. Okay. Now a definite integral is a function because you plug in something and you get one value out, right? But eventually you kind of relax that restriction and you just say just things that map back and forth. You just call them functions just for, and here we're just calling them transformations, but that matrix, if it had a column of zeros, it does not have an inverse. All right, I kept it under an hour, so I'm proud of that. I think that's it. So thanks for coming.